Welcome to Chapter 4. We're going to start Chapter 4, and then we're going to do Chapter 5, and Chapter 5 we're going to split kind of in half. So, the main thing to remember about Chapter 4 is that it's going to feel a little bit choppy because we're also going to do part of Chapter 5. But one thing is, Chapter 4 is unusually wordy. It has a lot of history involved in it. You do need to know some of that history because it is pertinent to how we discovered the atom. So we're going to summarize in the notes. There are certain details you'll need to know. You won't have to know absolutely everything specifically. If I talk about it in the videos, you'll probably want to know it for the quizzes and for the exam, the midterm exam. Pay attention in class, make sure you do the assignments, and reading the book would actually be a really great idea for Chapter 4. So right now what I would like for you to do is draw a picture of what you think an atom looks like. So pause this and draw it. Okay, I hope you actually paused it. You probably drew something that either looks like a dot, or it looks like something, it looks like that, or it looks like something from Jimmy Neutron, or something from the Big Bang Theory, or something like that. So what we're going to do is we're going to talk about the historical development of the atom. And to do that, we have to start way back on a dark evening in ancient Greece, as Sheldon Cooper would say on the Big Bang Theory, and talk about the fact that the Greek philosophers sat around and thought a lot. And they talked about what matter was and the meaning of life. And what they decided was that matter was composed of things such as earth, water, air, and fire. And that is what matter was. Many believed that you could endlessly divide matter into smaller and smaller pieces. And you could just keep going down, and it just kept dividing. But then there was a dude named Democritus, and you will need to know his name. And Democritus was the first person to propose the idea that matter was not infinitely divisible. Not infinitely divisible. That's important because he called these atomos. He was the first guy to come up with the idea of the atom. And atom, you know the prefix from your Greek roots, a means not, and tomos in ancient Greek means divisible. So, the word atom actually means not divisible. And we're going to go with that for right now until we get to nuclear chemistry. So, Democritus said, this is not right. At some point you have to stop being able to divide. And then there was a guy named Aristotle, and you probably heard of him. But Aristotle disagreed with Democritus because what he didn't believe is that you could have empty space. And since Aristotle is probably the one that you have heard of before, his views went unchallenged for 2,000 years. So from about 300, 400 BC until about the last 200 years. For those 2,000 years, humans believed, most humans, recorded history, believed that we couldn't divide. We could just keep dividing and keep dividing. Until the mid-1800s, when we developed methods to test validity of ideas. Remember, the scientific method. Pose a question, write a hypothesis, and then conduct an experiment. Well, it wasn't until about the 1830s that we had ways to actually conduct experiments that would be needed to check for the existence of an atom. So, Democritus and Aristotle, this is just kind of their ideas about matter. So, Democritus is the one that we like his ideas, but Aristotle was the one that everybody believed. Then there was a guy named John Dalton, and what John Dalton did is he did numerous chemical reactions, he conducted lots of experiments, and he came up with something that is now termed as Dalton's atomic theory. And so what it did is it explained the law of conservation of mass, going back to chapters 1 and 3, the law of conservation of mass in a reaction. So what happens, remember, the law of conservation of mass. Mass is neither created nor destroyed, it is only conserved or transferred. So, why is it only conserved or transferred? That is because you have combination, separation, or the rearrangement of atoms. So Dalton came had a lot of these chemical reactions, and he kept noting the same things happening over and over again, and came up with, again, revived the idea of the atom. So this was his atomic theory. Matter is composed of extremely small particles called atoms. That is correct. Atoms are indivisible and indestructible. That was proven incorrect in 1945 with the atomic bomb. Atoms of a given element are identical in size, mass, and chemical properties. We're going to talk about how that's mostly correct, not completely. Atoms of a specific element are different than those of another element. Yes, that is correct. Different atoms combine in simple whole number ratios to form compounds. That is correct. And in a chemical reaction, atoms are separated, combined, or rearranged. That is correct. So 4 out of 6 isn't that bad for a guy in the 1830s who didn't have much scientific instruments to go on. So he came up with atomic theory and revived Democritus' idea of the atom. So we call an atom, and it is defined as the smallest particle of an element that retains the properties of that element. So that would be the smallest particle of oxygen that acts like oxygen, the smallest particle of gold that acts like gold. You can have a gold atom, you can have an oxygen atom. They're going to act differently, but they're still both going to be atoms. And we can use what's called a scanning tunneling microscope, STM, to allow individual atoms to be seen. We do not have one of those at Lipscomb, but I believe they have a couple of them over at Vanderbilt. So, the very first subatomic particle, there's 3 parts of an atom. The first subatomic particle is called the electron, and it was found in a cathode ray. So a cathode ray is a ray of radiation that travels from the cathode to the anode of an electrical circuit. What a cathode ray is it's a stream of particles carrying a negative charge. So if you've ever seen one of those old fat televisions, like what I grew up with and what your parents grew up with and what your grandparents grew up with, if you open the back of that television, it had a cathode ray in it. And the cathode ray tube, it went from the cathode to the anode, and there would be a stream of negatively charged particles. And in that stream, what that stream is it's just a bunch of electrons going from the cathode to the anode. So the particles that carry the negative charge are known as electrons. That's our first type of subatomic particle. So number 1, electrons, they are negative. And we found them by doing experiments using a cathode ray tube with the cathode ray inside. So this is what a cathode ray tube looks like. The particles go from the cathode to the anode, and that green part right here that you can see, that would be where the electrons are. So the guy who found the existence of electrons, who is credited with that discovery, is a guy named J.J. Thomson. And basically what he did is he used magnetic and electric fields on the cathode ray to just figure out how big the particles were in the cathode ray tube. And he figured out it was a really, really small particle, much smaller than hydrogen, which is the smallest atom that we know of. And he received the Nobel Prize in 1906, I believe in physics, it might have been in chemistry, for identifying the first subatomic particle, the electron. So that's number 1. Well, matter is neutral. If you've got a negative electron, there's got to be something positive. So Thomson came up with the plum pudding model. And plum pudding is this English dessert, and if you like plum pudding, that is great. I think it's a little strange, but it's basically like this solid pudding kind of thing, but it's not like chocolate pudding, and it's plum pudding, and it has like raisins scattered throughout. So what Thomson hypothesized is that the atom is kind of like a container of pudding, And if you had the chocolate pudding and the chocolate pudding was positive, and then you scattered raisins throughout it, and those were your electrons, and it was negative. So since we know matter is neutral, we know electrons are negative, we were hypothesizing, okay, what else is in here that makes things positive? So the plum pudding model is right here, it's drawn, is that the kind of grayish part would just be like the positive pudding, and the electrons would be like the raisins that are scattered throughout, and they would be negatively charged because we know matter is neutral. And also there's a guy named Robert Millikan, and basically what he did is he took Thomson's knowledge, or the knowledge he gained from Thomson's research, and basically said, yes, the charge of an electron is negative. So, we know that there's some negative electrons hanging out in the atom. We know matter is neutral. So we know there's got to be some positive things hanging out in the atom. So about 5 years after Thomson got the Nobel Prize, Ernst Rutherford kept studying how these positively charged alpha particles interacted with solid matter. And basically what he did was what we now call the gold foil experiment. And when he took a sheet of gold foil, very thin gold, and shot alpha particles at it. And alpha particles are positively charged, and it would basically be like taking a BB gun and shooting it at a paper target. And so what he expected to happen is to aim the particles at a thin sheet of gold foil, and for those alpha particles to only be slightly altered by a collision with an electron. So this would basically be like you taking your BB gun, hanging up your target 20 feet away from you, and you're going to shoot your BB gun at the paper. What do you think is going to happen? Well, the BB pellets are going to go straight through the paper. Well, what ended up happening is that most of them went through the gold foil, but a couple of them started bouncing back at him. So this would be like if you took your BB gun and you shot it at the piece of paper, and when it kept hitting the center of the paper, instead of going through the paper, it came back at you, and you're like dodging BB pellets, and you're like, what's going on? And they started coming back at large angles. And when they started coming back at large angles, Rutherford was confused. And so what he ended up hypothesizing is that atoms are mostly empty space. And we agree with this. Atoms are mostly empty space. And that almost all of the positive charge and almost all of the mass is contained in a dense region in the center of the atom. This is called the nucleus. So we went from the plum pudding model where the whole thing was positive with random negatives scattered throughout, and now we're going to what's called the nuclear model, where you have a nucleus in the center of the atom, and that's where the positive charge is basically. And you've got the electrons that are negative scattered throughout. The electrons are held in the atom because they are attracted to the positively charged nucleus. Matter is neutral. So if I'm going to look at this, even though we're taking the plum pudding model and we're altering it, this is science. We take what we know, we do more experiments, and we shift our mindset. So what was happening was those alpha particles, your BB gun pellets, what they were doing is they were hitting the nucleus and bouncing back because they were the same charge. So this is now, oh, hello Apple, you can stop updating. So this is now what we think of as the nucleus in 1911, 1912. And so we call these protons. So we have electrons, and they are negatively charged. We have protons, and they are positively charged, and they are in the nucleus. And then in 1935, 20 years later, James Chadwick found our third and final subatomic particle, and it is called a neutron. And they are neutral, and they account for the rest of the mass. And this is important or the nuclear bomb. Thanks for your attention, and right now I want you to write down the 3 subatomic particles found in the atom. Thanks.